Good day, guys. Alright, thank you very much for watching my channel. My name is Renato Robles. I'm a Cisco CCNA network engineer and junior Python programmer, and we will be talking a little bit about quality of service. Very important subject, very practical, useful subject because we can improve the quality of the service. Whenever we're working with traffic coming from multiple sources, if we have multiple computers connecting to a switch, and then those switches to a router, and then those routers exiting to the internet, we can start finding congestion, especially whenever we're handling multiple different packets coming out of multiple different applications. Some of the traffic is actually more important than other types of traffic. For example, if we're doing a phone call and we want to ensure that we talk to the customer, if he's a very important, or she is a very important customer for our company, we're about to close a deal, we're about to convince some important people to be part of our project. We want to make sure that the quality of that service, the quality of that call, is actually the best possible. Same thing with video conferencing. If we're doing a conference, we want to make sure that the other person is able to see the image properly, they're able to listen to us. So we need to know how to avoid delaying too much those packets. We need to know the nature of those types of packets. We need to know the ports. We need to know how to configure our switches and our routers in order to make sure that we have a good quality of service on those applications, for WebEx applications, Skype, Zoom, of IP phones, all of those types of traffic. They are also called priority traffic. And we also may have some other critical traffic as well, coming out of other different applications that we want to make sure maybe they have a secondary type of priority, making sure that we get the information on time as well. For example, we could have a special application residing in our databases, maybe Oracle databases, many other things which are also critical for business. A ticketing system, for example, that usually is very important, especially if we have outage related or very critical type of tickets that we need to handle. We want to make sure that that information is also timely serviced. So this is where quality of service comes. And then there is another type of traffic also called scavenger type of traffic, and we can give it a best effort type of priority, which is just the lowest type of priority. That's, for example, Facebook, YouTube, any other type of application that is less important than the most important of our applications, of our information. To that type of data, we can give it at the lowest priority available. All right. Also, we have to take into account some specific details about the type of data that we're working with. So, for example, with voice, we know that we're using UDP in the layer 4 or in the transport layer, which means there's no three-way handshake. The information is sent and the packets are smaller, which is a good thing. They are much smaller than TCP, so they can be processed much faster. We can have a bigger load, a greater load of packets when TCP is a bigger packet, due to its nature of having the acknowledge bit, the synchronization bit, the TCP three-way handshake, all of that, the windowing information, all of that makes the TCP packets vary, or segments, technically speaking, much greater in size. So we have to consider that too whenever we're talking about IP phones, voice and data, which are delay sensitive information. Those types of data use UDP, all right, which means we have to send them in a timely manner too, in order to avoid losing any packets. If the packets drop, they're just dropped, basically. the conversation or whatever we're doing at that moment may be affected, and that information is lost. The person has to repeat whatever they said if some packets were lost. And whenever we're talking about, for example, TCP based applications, we can drop some packets intentionally because they are typically much larger and they can recover. The three-way handshake nature helps us recover that service later on whenever there is more bandwidth available. And that's when we start talking about policies like such as policing and shaping. All right, where we drop some packets intentionally, that's called congestion avoidance. Whenever we start sensing that the bandwidth is being occupied too much, we establish a minimum and a maximum thresholds, and that's where we take advantage to put some packets on the queue. We can put even some limit to the packet queue, also to make more efficient the use of the processing of the queuing. We can do some tail dropping or even policing, where we just drop the packets, and that's something we'll be talking about later on. The TCP protocol in the layer 4 allows those applications to recover later on. The packet will be resent. All right, the packet will be resent if there's an absence of an acknowledgement bit. The other host that we're sending the information to will actually acknowledge that the resend needs to happen, and that's when we resend, or well, the device will automatically resend those packets accordingly, right? That's the advantage of TCP type of data. We can just drop some packets to alleviate a little bit of the bandwidth and avoid the starvation of more critical UDP, usually UDP types of packets or segments. So quality of service. It is the traffic prioritization and measure of network performance. All right, that's the official definition. All right, we're reading Wikipedia. Traffic prioritization. So, for example, voice, critical data, and then also measure of network performance. We have some protocols available on the networking devices that helps us to also detect what type of data is traversing our network. Sometimes it can be an overwhelming type of different types of packets. So there are some protocols that helps us detect the different applications that are in use, the corresponding ports, and sometimes even create some nice graphics that helps us detect what type of traffic utilizes most of the network bandwidth in a certain moment of the day. That helps us decide based on their nature of the if it's UDP or TCP type of packet, and the amount of information, the amount of bandwidth that it's occupying at a certain moment, if we will apply certain policies to them. All right, so that's why we have here measure of network performance. That's quality of service altogether. It is a description or measurement of the overall performance of a service, such as telephony or computer network or a cloud computing service, particularly the performance seen by the users of the network. To actually here, that's pretty important, to particularly to the users, seen by the users of the network. This is why QoS is relative to every company that utilizes. It depends on the business needs. Basically, that's how it's technically described. Meaning, depending on the nature of the business, we will need to apply certain policies to certain traffic. For example, there are companies where voice over IP is the most critical information most of the times. That's what happens. But then there are companies where that's actually less important, and there are other types of data which are more important than those. In those cases, we will actually configure the devices to prioritize that type of critical data. So it depends on the business need of the company. Also, we could have, for example, some directors or even the president of the company, and they want to get a special priority everywhere they go, regardless of maybe other types of data that are traversing the network. That's also depending on the company and on the decision of the decision makers of the company. All right, so that's where we have to adjust the settings of these devices to meet those needs. So that's where we see quality of service being applied, seen by the users of the network. So it's a very human thing. All right, that's how we will say it. It's a very human type of decision and experience. To quantitatively measure quality of service, several related aspects of the network service are often considered, such as packet loss, bit rate, throughput, transmission delay, availability, jitter, etc. So these are important data that we consider. Of course, basically what we're considering most of the times is the bandwidth, because as a general rule, if we are experiencing too much delay and a great deal of information, the solution really is to increase the bandwidth, which means buying more powerful equipment, buying more powerful interfaces and cabling. That way we increase the bandwidth power, and the cabling and the devices are actually able to interface a greater deal of information, therefore resolving our problems. But most of the times, what happens in companies is that they want to save as much money as possible, of course, and they want to we want to save as much money as possible in the companies, and we also want to use the equipment that we currently have in the most effective manner. All right, we want to squeeze every drop of possible bandwidth that we have. Okay, all right, that's before we buy anything new. Before we buy anything new, we want to take advantage of what we have first, the best way possible. That's a basic economical principle. Yes, if we bought some equipment and maybe we have a bunch of Facebook traffic, which is occupying a lot of the bandwidth, why would we buy bigger equipment, bigger bandwidth to get a greater bandwidth, if we can just stop all of that non-critical data from going through? All right, that's a good question. We can just stop Facebook for a while, decrease the amount of bandwidth that those applications are using, and give priority to the most important things. That way we save money on the company. And that's where we start talking about packet loss. Packet loss. How many packets are being lost in a certain moment? Normally, if we don't apply QoS specifically, actually QoS is applied by default in the form of FIFO, first in, first out. The first packet that comes in, the first packet that is sent to the other side. And whenever that happens, if the bandwidth starts being occupied and congested, if it's congested, that's when we start dropping all types of packets, because we're sending pretty much as they are arriving. We start dropping voice packets, video packets, application packets, all of them all together. So that's where we sometimes prefer to drop establish policies that drop less important traffic and allow more important traffic to be sent over. Packet loss, that's why it's important to study that. Bitrate. Bitrate pretty much is the bandwidth. Why? Because bandwidth is measured in bits per second. And rate talks about the constant speed, so that's measured in seconds. For example, if we're talking about 1 gigabit interface, or fast Ethernet, which is 100 megabit per second interface, we're actually converting it to bits in order to do the proper calculations, which is for 1 gigabit, we're talking about 1,000 million bits per second. And then once we have that data, we can actually perform some calculations in order to find out the minimum and maximum thresholds on the use of that bandwidth, and therefore apply the policies whenever a specific amount is being utilized. For example, if we want to know the 10% of the use of the bit rate of a specific interface, we would do the conversion. If the interface is 1 gigabit per second, a 1 gig interface, as is known normally on the field, a 1 gig interface, that uses 1 million bits per second. Then you have to divide it by 10, which gives you 100 million bits per second. So then we know that the 10% of 1 gig is 100 million. We can establish a policy. Later on, we will see how it's configured. We have multiple quality of service mechanisms that we can configure on the devices. Based on that information, we can say, all right, so at whenever we reach the 10%, we establish that as the minimum threshold. Whenever we reach a 20%, or maybe that's too low, probably 50% of it, or even 70%, we establish the maximum threshold, and there are some specific actions that are taken once we reach that amount of use of the network. All right, if we start getting congested, that's relative to us. Remember, that depends, the congestion on the network depends on the user experience. So that's why bitrate is important to know, because at the end of the day, we're making the use of the bitrate of the bandwidth the more efficient possible in the field. Throughput is basically talking also about the bandwidth, but a full duplex, from a full duplex perspective. All right, throughput means whatever information is going out the interface and coming in. As we remember, whenever we're talking about straight through or crossover cables, fiber cables, we have full duplex. That's throughput. We need to know that the information as it's sent, it's actually also received. All right, full duplex. Transmission delay. There are multiple types of delays. In the official Cisco website, there's a lot of emphasis about learning the delay. Also in the official CCNP book from Cisco Press, a lot of emphasis on transmission delay. We have multiple types. For example, there's a refraction delay, where naturally happens in copper cables and fiber optic cables. The cables come with the refraction value. That's something that the hardware engineers determine, and they print it on the cables. We have to be able to read the specifications of the cables, and we can do some calculations in order to determine what will the cable delay, the physical delay, be depending on the technology that it uses in the hardware physical layer. So for example, I know a calculation which comes from the official press book, Cisco Press. It says the speed of the light in seconds, in meters per second, is normally 200,000 million. All right, and then if we divide it by the refraction delay, we will get the speed that the data will have when we use that specific type of cable. And then we have to consider the distance in meters, where if we connect a cable to a networking device on one side and another networking device on the other side, the distance of the cable divided by the speed of the cable gives us the refractory delay. That's it. It's just a formula, division and then division again. That's one question, possible question on the test. There's many engineers who have said that yes, they actually got some questions on the tests about that type of delay. Then we have other types of delays which are important to consider, because those kind of delays are just physical depending on the type of cable that we're using. But there are some other types of delays that have to do more with some things we do on the quality of service. For example, if we establish a policy where some of the packets will be queued, they will be placed on the queue, and just give a preference to, for example, voice over IP type of packets. The packets that we placed on the queue, let's say for example file type of packets, maybe we have an FTP application, we can put those packets on the queue. Then there will be a delay, naturally, because we're placing them on the queue. They're waiting until our other more critical types of packets are sent, and that's called intentional delay. That's where jitter also could occur if some voice packets are delayed due to the bandwidth being already occupied too much. So if some voice packets or video packets take a while, probably 100 milliseconds to 300 milliseconds maximum, then we will experience a delay. All right, that's where we start hearing the other person voice cutting out, or if they say something, suddenly it reaches our side later on. All right, those types of problems make us step one another. So I talk, but then it takes a while for them to hear me, so then they start talking at the same time and it becomes a mess. All right, naturally, whenever jitter happens, there is a special mechanism which is intentionally designed and installed in Cisco phones, for example, in order to avoid that type of delay. All right, that's jitter avoidance, a jitter avoidance mechanism. Cisco IP phones can retain voice packets up to 300 milliseconds, then they're dropped, and those type of questions also come in the test. So those are delays we have to consider. There are some other two types of delays, which is processing delay and serialization delay. Processing delay happens depending on the power of the devices that we're working with. So, for example, we have some routers and switches, certain models. They could be catalyst switches, they could be nexus switches, which are more powerful for data center type of information. They will have more powerful processing. They have more RAM, they have better RAM, they have better processing power, and depending on that, there will be a certain specific delay. That's depending on the powering of the processing power of the devices. And then serialization delay, that's just a technical term that refers to the amount of time that it takes for multiple packets to actually go back together and form a specific type of application information all together. So let's say, for example, a photo. The photo will be pretty much cut out in multiple pieces, multiple packets, and all of those packets and segments and frames will be sent over, and whenever they reach the other side, they start being serialized according to their to the order that they should be placed, all placed together. There's a serialization delay until we get the complete enchilada. I mean, the complete picture that was sent over initially. All right, so now availability. That's also talking about quality of service. It's about the availability of the bandwidth. The same thing. It's pretty much the same concept. If we think in terms of energy, we will get the keys of the universe, right? Nikola Tesla. So if you consider, if we think in terms of bandwidth, bits per second, all of these things are explained in terms of bandwidth. All right, bits per second. All of these concepts: packet loss, bitrate, throughput, transmission delay, availability, and jitter. All of them are just different faces of the same thing, of the bandwidth. Availability talks about the available bandwidth in a certain moment. All right, so in the field of computer networking and other packet switch telecommunication networks, quality of service refers to traffic prioritization and resource reservation control mechanisms rather than the achieved service quality. That's the technical part. All right, so whenever we start talking about the technical part of the equipment itself, that's what we get. All right, that quality of service is technically for the routers and for the switches, independently of the business need of the persons. What they understand is just a bunch of rules that they have. All right, they are, in a way, we can say they're careless of our business needs. They just do what we tell them to do. So to them, quality of service is the traffic prioritization. Very squared, very cold type of seeing the situation. All right, they're just the mechanisms for reservation control. All right, and here it just talks reservation in general because to avoid confusing it with the RSVP protocol, which is reservation control protocol, that's something else. Quality of service is particularly important for the transport of traffic with special requirements. That's the same thing we were talking about. Voice over IP has special requirements. It has to have a delay normally less than 200 milliseconds. It's still acceptable. In particular, Developers have introduced voice over IP technology to allow computer networks to become useful as telephone networks for audio conversations, as well as supporting new applications, even stricter network performance requirements. So yeah, you can define policies to whatever information you believe is critical to your business. Basically, that's what it says. Definitions. In the field of telephony, quality of service was defined in the Telecommunications Unit in 1994. It comprises the requirements of connection, such as service response, loss of packets, signal to noise ratio, those things, also consequences of delays. Crosstalk, remember when we said some packets arrive later and then you start crosstalking or talking on top of the other person. Echo, same thing, delaying of packets. Interrupts, because some packets just delay too much and then they arrive suddenly and the other person's already talking, etc. Same thing. Frequency is just the same thing, because it's about the that's the same thing but in hertz. That's visualizing it from the energy point of view. What is the frequency of the packets arriving on the line? Response, loudness levels, and so on. All right, all of those things. A subset of telephony QoS, quality of service, is grade of service requirements. All right, so in the field of computer networking and telecommunication networks, teletraffic engineering refers to traffic prioritization and resource reservation control mechanisms rather than the achieved service quality. That's just the technical perspective. Quality of service is the ability to provide different priorities to different applications, users, because you can apply quality of service based on users. How is that? You can define, whenever we go to configure quality of service, you can take into consideration the MAC address of the device. For example, if there's a specific MAC address connecting to a switch, that MAC address will be prioritized. All the traffic coming out of that computer can have a priority queue, for example, so that all the information that is sent or received from it, we ensure it reaches the destination. That happens when we have very critical people connecting on the network. All right, we establish based on users. We can also do priorities depending on the applications. There is a detection technology, helps us identify over 1,000 different applications. All right, over 1,000 different applications and their corresponding ports to give them the priority accordingly. Data flows. Data flows is a group of it. So for example, I can say voice and video conferencing and even management type of data will get a specific flow identifier, and that flow will get a specific number or priority. All of them will be treated equally. Different types of protocols are placed into a data flow, marked as a specific data flow, and they all will get the same priority that I establish for them to have, or to guarantee a certain level of performance to a data flow. For example, a required bit rate, that's the speed, a required bandwidth, a delay variation, packet loss, or bit error rates may be guaranteed as well. Quality of service is important for real-time streaming multimedia applications such as voice over IP, multiplayer online games, especially whenever they're competing, right? That's when video games become important, because, for example, if we're at a call center type of office and some guys are actually playing video games online, come on, that could be the least important type of data traversing the network, of course. But if you go to a competition where you're talking about the best players in the world competing in a tournament where there's $1 million prize that we will get, of course, we want to ensure that that data has the highest priority, because there we're talking about sport, all right? So it depends on the situation again. Multiplayer online games, they can be the greatest, they can have the greatest importance, and therefore the greatest priority. And IPTV. Since these often require fixed bit rate and are delay sensitive, quality of service is especially important in networks where the capacity is a limited resource. For example, in cellular data communication, there is CCNA, actually double CCNA, who says, he explains how even the highest speed networks, like you can have very powerful devices, all right? You can have the 10 gigabit per second interfaces, very, very fast. But even in those situations, if you're talking about a data center, for example, that's actually Kevin Wallace who says it, double CCIE. If you have, for example, multiple interfaces in the access layer, and all of them are sending data simultaneously, and then on the other side you have an exit interface, which is just one exit interface, also high speed, 10 gig per second, it gets overloaded. There is congestion on that interface because it's getting the input from multiple very high speed interfaces. So you might need quality of service even in high speed networks, especially in data centers. Quality of service is especially important in networks where the capacity is a limited resource. A network or protocol that supports QoS may agree on a traffic contract with the application software and reserve capacity in the network nodes, for example, during a session establishment phase. That refers to the RSVP protocol, all right, reservation protocol from Cisco, which basically means that an application from a computer can reserve some bandwidth. The counterpart of that is that the bandwidth is reserved, yes or no. Even if it's used or not used, the bandwidth is reserved, and no one else can use that bandwidth unless the application releases it formally. That's the problem with RSVP protocol. Another problem with it is that the end device, the host that is reserving based on the application, they need to send constantly RSVP messages, which can flood the network with RSVP requests. And there are some also RSVP refreshing packets, special for maintaining the reservation. Otherwise, the reservation is lost. All right, so that's RSVP. In the official Cisco press book, CCNP press book, I recommend you reading that one. It tells you a big overview of it, pretty well explained. And what we use, that's actually part of the integrated services, quality of service mechanisms. But we have also DiffServ, differentiated services mechanisms from QoS, where instead of doing that type of reservation and using RSVP packets, we can use a more scalable and efficient mechanism, which is differentiated services with weighted for queuing and weighted red, congestion avoidance, for example. There are other mechanisms, but basically what happens with those is we will mark the traffic with a specific priority. That's where we start talking about classification and marking, and we can mark the traffic on the layer 2 and layer 3. All right. And what happens there is that we will have per hop behaviors. So all the devices on the network will be configured with a specific quality of service policy mechanism. And as soon as the packets arrive and the frames arrive, certain actions will be taken on them. The policies will be applied accordingly depending on the monitoring, internal monitoring of the device, of the network at that specific moment. So, very interesting subject. That's more scalable, differentiated services. Now, during the session, it may monitor the achieved level of performance, for example, the data rate and delay, and dynamically control scheduling priorities in the network nodes. All right, and so that's where we start having different mechanisms. We start having weighted for queuing. We can start having class-based weighted for queuing, and then low latency queuing, which is LLQ. They start becoming more and more complex because weighted for queuing basically creates multiple different queues for different types of data, and those are serviced according to their priority field. All right, so the lower the number, the longer it takes for the packet to be serviced, and the higher the number, the faster and the more packets will be served from that specific queue. There's a formula from the book, which is basically the number that we set on the class of service field, on the class identifier, if it's layer 3, in the DSCP field, even IP precedence field, and depending on the EF or AF values and the priorities, the formula says multiply that number or divide that number between the total of the values of the priorities set for the specific QoS mechanism that was established. All right, so for example, if we have a packet arriving and it's placed on the priority 5 queue in terms of congestion, then if we get other packets with a priority 1 from a lower priority queue, then we will send 5 packets and then just 1 packet from the lower priority queue. All of those packets that have a 5 priority will be pretty much sending 5 packets and then sending 1 packet from the lower priority queue, and then again 5 packets from the number 5 priority, and then just 1 packet from the lower priority queue. That's how weighted for queuing works in general. There's a formula to be more precise, but in general that's how it works. Then class-based weighted for queuing, we establish classes for specific flows of data, and same mechanism pretty much, weighted for queuing. And that can be, there's a metaphor to explain it to you, which is nice to understand the concept. And that is that if you have, for example, a balloon, and that balloon you fill it up with some helium gas, all right, helium gas, it will float, right? And then, well, we try to be ecological, so hopefully those balloons are ecological. And then what happens is the more helium you give it, the more that they float, right? And the lower amount of helium you give to the balloon, the more they will tend to be stuck at the bottom of the recipient, wherever you have them, right? So the ones with the higher amounts or the higher number will go out first, and the ones with the less amount of helium will stay at the bottom for longer. They will wait more, and vice versa with the drop probability field, which is another type of field that we have in DSCP, where we have 3 types of priorities. There it is actually backwards. the greater the number, the greater the probability for the packets to be dropped in drop policy, in QoS drop policy mechanism. All right, or QoS, if that's what we're applying. So it's actually inversely proportional up to the number 3, because we have only 3 possible values for that drop probability field. All right, so then we have the low latency queue, which is the same class waited for queue mechanism, but we add the priority type of traffic, where, for example, voice over IP will get that priority, and those packets will be sent definitely. All the other queues will just wait. All right, they'll just wait until voice over IP is, all of the packets are sent, all of them, regardless of the amount of it. And that happens whenever we establish that threshold mechanism. All right, from that point, that's what happens. And whenever the line is decongested already, we have a normal policy, probably waited for queuing, class-based waited for queuing, or just first in, first out if it's less than the minimum threshold. For example, the data rate and delay and dynamically control scheduling priorities in the network nodes. That's it. That's just priorities is policy. Applying policies, applying the QoS mechanism. It may release the reserved capacity during a tier down phase. Yeah, basically those things happen when there's congestion. Once congestion is released, we go back to a normal type of service, best effort. A best effort network or FIFO or service does not support quality of service. An alternative to QoS control mechanisms is to provide high quality communication over best effort network, or over provisioning the capacity so that it's sufficient for the expected peak traffic load. That's when we sometimes just buy better equipment to improve the bandwidth. The resulting absence of network congestion reduces or eliminates the need for QoS mechanisms. So yeah, if you have better equipment, like more powerful equipment, normally you start handling all the data that you need. And then why applying QoS? Sometimes with very powerful interfaces, very powerful networks, we just use them as they come by default, FIFO, first in, first out. QoS is sometimes used as a quality measure with many alternative definitions, rather than referring to the ability to reserve resources. Quality of service sometimes refers to the level of quality service. For example, the guaranteed service quality. All right. Now it starts repeating many things. Here's the history, of course, whenever it was created. But I love this article because it explains pretty clearly. Good put. Sorry, it explains very clearly all of the general view of why QoS is used. Why do we even need QoS? And then we can go to the Cisco Pressbook, or even to the Cisco official website, where they have the guide for QoS. Very, very well explained too, for all the technical nitty-gritty details. We learn how to apply the quality of service mechanisms, and we know the technical details of the packet marking, packet shaping, packet policing, all of that. All right, so well, let's go ahead and continue with the next video, where we'll be talking we'll be reading the QoS Cisco guide. All right, thank you. I hope you enjoyed. Have a good day.